and welcome to Night Sky News with me, astrophysicist Dr. Becky. This is the series where we chat about everything you should look out for in the night sky in the coming month, and we chat about what's been going on in space news in the past month. So let's kick off this episode for February 2021 and start by looking up. So last month I talked about the winter hexagon, the 6 bright stars that ring the constellation of Orion. And I heard from so many of you that you'd managed to go outside and spot it for the very first time. So I thought I'd highlight it again this month for all of you who want to see it, but you're not necessarily sure what you're looking for. Because there's going to be a half moon smack bang in the middle of it on Sunday, the 21st of February. Now, it should be very easy to find the moon. And then from there, look out for the 6 bright stars around it. If you start at Rigel, which is just below Orion's belt, which I know a lot of people are able to recognize. If you start from there, go down to Sirius, then up to the star Procyon, to Pollux, up to Capella, right at the tippity top, and then down to the red star Aldebaran and back down to where we started at Rigel. Spot this while you can, because the changing of the seasons means that in the northern hemisphere at least, we're not going to be able to see this in our night sky for much longer. So you might have noticed it's been setting earlier and earlier as the days march on. But in its place, we have the summer triangle instead, and that's beginning to make an appearance in the very early morning sky just before dawn. Again, like the winter hexagon, this isn't an official constellation. It's just a really easy pattern of stars to pick out in the sky because they are so bright. In fact, if you look to the east before dawn, so whatever window of your house tends to get the morning sun and that you can see the sunrise from, you should be able to spot these really easily because they're the brightest stars. So they'll probably be the only things left that you can see against the brightening of the sky with the sunrise. So the 3 stars are called Deneb, Vega, and Altair. And now I've pointed it out, you won't be able to unsee it. Back to the evening sky for a little bit though now, because on the 3rd of March, Mars is going to get really close to the star cluster Pleiades. It's going to be about 2.5 degrees away from it, which is about 5 full moon distances, which sounds pretty far, but actually in terms of the sky, it really isn't. It actually means that if you grab a pair of binoculars and look at Mars, you should be able to see both Mars and Pleiades at the same time with a pair of binoculars. It's the closest together that Mars and Pleiades have been on the sky from our perspective since 1991, and they won't get that close again until 2038. So it's definitely something that you want to go out and try and catch. So no matter where you are in the world, if you look for this in the evening sky, so just after sunset, quite high in the southwest, and you find Orion's belt and use it to draw a line up to Pleiades, where you'll see about, 6 to 8 stars clustered together looking like a beautiful little mini plough or a big dipper, and next to it will be the unmistakable red glow of Mars. Then on the 9th, the 11th of March, which is about a week later, we're going to have a toenail moon or a crescent moon, which is pairing up with Jupiter, Mercury, and Saturn in the early morning sky. Now, the moon and 3 planets really will be a spectacular sight, but not all of us will probably get to spot it. The further south you are, the better, as the planets and the moon will be much higher in the sky. Whereas here in the UK, we are just a little bit too far north for me to have any hope of spotting this, right? It is still winter here, so, the North Pole is still pointing away from the sun and therefore away from the part of the sky where the moon and Jupiter and Mercury and Saturn will all be, because this is so close to sunrise that you need to look for this. But if you are further south and you do manage to spot this, then make sure you take a picture and send it to me on social media, because I love a good toenail moon. But the other reason to take a picture is because you might actually struggle to pick out Mercury with your eye. It is going to be a lot fainter than Jupiter and Saturn, and obviously the sun is rising quickly behind this as well, so the sky will be lightening, making it even more difficult to spot. But if you break out your phone and you take a 3-second or a 10-second exposure on a night mode, like a lot of phones are able to these days, or you grab a bit more of a sophisticated camera perhaps, then snap a pic, see if the camera can pick it out as well, and you'll be able to spot Mercury that way. Speaking of Mercury, now is actually the best time to try and spot it, because on March 6th, it reaches its furthest position from the sun, from Earth's perspective anyway in the sky, what we call its greatest elongation. What that means for us is that it'll rise higher in the sky before the sun rises quickly behind it, right? Because that's the problem with Mercury, is that if you're looking in the direction of Mercury, you're also looking in the direction of the sun as well. And because it is quite small, it is very faint. But luckily, throughout about March, Jupiter is going to be very, very close to it, which is a really nice signpost of where to look, because Jupiter is so much brighter. It's one of the brightest things in the sky. So if you can find Jupiter towards the sunrise, you can then sort of hop from there to find Mercury. All right, that's enough at looking up at the sky. Let's come back down to Earth and chat about what's been happening in space news in the past month. So another month, another SpaceX Starship test, and another explosion. So Starship is SpaceX's new reusable heavy lift launch rocket, the kind that could launch humans on long journeys through space and perhaps even be used as a reusable moon landing system. This was its 7th test and its second high altitude test after the one they did back in December. And like that one back in December, the launch and the flight went great. It was just the landing that didn't go to plan. This time, one of the engines actually failed during that flip maneuver that it does to rewrite itself so that it can self-land and be reused. And obviously, instead, that led to a crash landing. Now, a crash landing, though, isn't a failure, right? You learn so much when things go wrong as opposed to when things go right. So the team will make all of the necessary adjustments in time for the next test. It was all success, though, for the HOPE probe and the Tianwen-1, which last week both successfully arrived at Mars, changing their trajectory to orbit around the red planet. Now, the HOPE probe is the UAE's very first mission to Mars, and the plan is for it to stay in orbit around Mars so that it can study daily and seasonal changes to weather patterns on Mars, and in particular study the dust storms that can grow to be planet-wide on Mars. And it's these planet-wide dust storms that have always been a real danger to any mission to Mars, whether that is a robotic mission or whether that is a crewed mission to Mars as well. So it's very important that we know more about those. Now, the Tianwen-1 is the Chinese National Space Administration probe, and it has an orbiting probe, a lander, and a rover. Now, its mission is to search for evidence of both current and past life on Mars. And it's going to do that through a combination of things. So from very detailed surface maps to making maps of the distribution of the ice on Mars as well, to soil samples, to studying the atmosphere, all through, the orbiter, rover, and lander all working together. Now, they're not going to attempt to actually land the lander and rover on Mars until May 2021, unlike NASA's Perseverance mission, which will actually arrive at Mars on Thursday, the 18th of February at 3 p.m. East Coast time in the US and actually land on the same day. And I know I am going to be watching the live stream from Mission Control on that day because I just want to be present for that 7 minutes of nail-biting terror as the craft descends through the Martian atmosphere at 12,000 miles an hour. And you've just got to keep your fingers crossed that everything goes smoothly and the parachute comes out all right and you end up with a soft landing and not a crash landing, because we want this craft to survive. Because one thing that I'm so excited for on the Perseverance mission is the little mini helicopter it's carrying called Ingenuity. It's a little bit like a drone, I guess. It's a complete proof of concept. It's never actually been done before to achieve flight in, Mars's thin atmosphere. But what it would do is just make exploration of the surface of Mars much easier, because it can go places that Perseverance, the rover, which has been nicknamed Percy, which I love, they just can't go. So it'll help it on its mission to, look for these current and past signs of life, again, what we call biosignatures, either in the soil or in the Martian atmosphere. But also one of the things that Percy will be testing is if you can actually make oxygen from the CO2, the carbon dioxide that makes up the bulk of the Martian atmosphere. And that really is just one of those things that will sort of pave the way, I guess. It's really sort of part of the preparations for maybe sending humans to Mars one day. Now, you're probably wondering why there's 3 missions all arriving at Mars at once, pretty much within 10 days of each other. It's like buses, isn't it? You wait for one and 3 turn up at once. But there's a good reason for it. It's all to do with the relative positions of Earth and Mars along their orbit around the sun when you launch the mission. It's something we call astrodynamics.
Astrodynamics.
Yeah.
So when you launch something to Mars, you don't want to launch it directly at where Mars is then, because in 6 months' time, when it gets there, Mars will have moved. So when you launch it, you want to launch it at where Mars is going to be. The thing is, though, that the Earth takes, 365 days to go around the sun. Mars takes 687 days. So the two are always sort of playing a little bit of a game of catch up along their orbit around the sun. So what you don't want to do is launch towards Mars when Earth is on one side of the sun and Mars is on the other side of the sun. You want to do it when Earth and Mars are on the same side of the sun and Earth is actually catching up to Mars a little bit. There's only a limited time, though, when that actually happens. They're called launch windows. For Mars, these launch windows occur every 26 months or so, and they last for about 3 weeks. The last one was from the end of July 2020 to the middle of August 2020. And so all of Hope, Tianwen-1 and Perseverance were all launched pretty much at the same time within that one launch window, hence why they're all now rocking up at Mars within 10 days of each other. Now, another piece of news I want to mention is the latest paper from the Dark Energy Spectroscopic Instrument Legacy Imaging Surveys, or DES for short. This is a survey conducted with the 4th Mayall telescope at the Kitt Peak Observatory in Arizona in the USA. Now, its main goal was to measure the redshift of tens of millions of galaxies out to a distance of about 11 billion light years away. And our redshift is a measure of how fast a galaxy is moving away from us. And the reason astronomers wanted that is because they wanted to study the expansion of the universe, and in particular, the accelerated expansion of the universe that's being caused by something we've dubbed dark energy, but we have no idea what that actually is or why it's causing this accelerated expansion of the universe. That's a problem for another day, though, because one of the exciting things that comes out from surveys like this, where you observe millions and millions of galaxies, is a load of serendipitous discoveries as well. And last month, Huang and collaborators on the survey team announced the discovery of 1,210 gravitational lenses. They use what's called a neural network to do this, essentially machine learning. It was training a computer on some known examples of gravitational lenses and getting it to identify similar looking objects. So a gravitational lens can be explained by Einstein's theory of general relativity, his theory to explain what gravity was. He said if things have mass, they curve space-time. The more mass an object has, the more that it curves space-time. And anything traveling along that space, for example, light or a planet or a star, will travel along a curved path. So if you have light from a very distant galaxy that's in the background pass by a very massive galaxy that's closer to us in the foreground that is bending space around it, that light is also bent, and you end up either with a ring if those two galaxies are perfectly aligned, or an arc if not. The foreground galaxy literally acts like a lens and changes the path of the light. Here's some examples of the ones that Huang and collaborators found with their machine. The red and yellow in the center of each image is the foreground galaxies, and then those little blue arcs or little points of blue light are from distant galaxies that have been bent or brightened by this gravitational lensing. And there's probably more of these lenses buried in the survey images somewhere, because these machine learning algorithms, they're not perfect. They don't pick out everything, and, they only pick out the things that you tell them to look for, not the things that you don't tell them to look for that might be sort of the weird and wonderful and new discoveries that we're maybe missing. But 1,210 new lenses is a huge number, and this database will be an absolute boon to those people who are studying, either dark matter or testing alternate gravity theories, seeing if these lenses can be, better explained by a different theory of gravity rather than Einstein's theory of general relativity, which then suggests there's loads of dark matter there. So there's going to be a lot of studies, I think, that come off the back of this new database that's been published. All right, on to the big news this month. Was it really phosphine on Venus? Now, if you cast your mind back to September 2020 and the hubbub that was created by the announcement of the detection of phosphine in the atmosphere of Venus. Phosphine is pH3, 1 atom of phosphorus and 3 of hydrogen. And people got very excited about this because it was unexpected, and crucially, it was unexplained. Now, the authors of this study, published back in September 2020, Greaves and collaborators, essentially ruled out all of the known ways of producing phosphine. So that was everything from sunlight to lightning to volcanoes on the surface of Venus. None of those could explain how much phosphine they claim to have detected. So essentially they said it was either some unknown geological process, or the other thing that it could possibly be is that there are microbes on Earth that don't need oxygen to survive that are known to produce phosphine. And even though they very tentatively stated this, of course people got way overexcited about it, as people all want to do when it comes to aliens, even if those aliens are teeny tiny microbes. I have to admit, even myself, I got very caught up in the excitement around it and even rewrote the lyrics to David Bowie's Life on Mars to be Life on Venus. Of course, the research paper never claimed they had actually detected life. All they claimed was the detection of phosphine. Now, publishing any scientific paper is sort of like a message to the scientific community to be like, please discuss amongst yourselves. Please scrutinize this work and maybe come up with some ideas of your own to explain what we've found here. And a paper that was published this month by Linkowski and collaborators is claiming that in the original study, Greaves and collaborators didn't actually detect phosphine at all, but that they'd analysed the data wrong and instead had just detected sulfur dioxide, the most common element in Venus's atmosphere. So to understand what's going on here, we really need to understand what actually was the detection that Greaves and collaborators originally made in that paper published back in September 2020. So what they did was they observed Venus with a radio telescope. And that's important because phosphine is known to absorb a very specific wavelength or color of radio light. So if you were to observe Venus and make a trace of how much of every single wavelength or color of light you detect, you would find a dip at this very specific wavelength. The deeper the dip you have, the more of that molecule or element or whatever it is you've got absorbing that light. Now, phosphine absorbs light with a wavelength of 1.123053 millimeters. The thing is, sulfur dioxide also absorbs radio light, but with a wavelength of 1.123058 millimeters. So the two, they're very close together. And when you observe it, your detectors aren't perfect, right? So the two can actually merge together if your detector isn't sensitive enough to resolve the difference between those two wavelengths. Now, Greaves and collaborators obviously knew this when they published their work back in September 2020. And it's one of the reasons they actually spent about 4 years making sure that what they were claiming was actually right, because they'd actually seen this back in 2016 in data taken with the JCMT. Now, obviously, they wanted to check that what they had detected was not just sulfur dioxide, and there actually was some phosphine in this dip as well, contributing to how deep it was. So what they did was they used a different radio telescope called ALMA to observe this again, make sure they saw this exact same dip where phosphine was expected to be absorbing. But also, crucially, they wanted to observe at a different wavelength, this time at 1.102564 millimeters, where sulfur dioxide also absorbs at, as well as the one that's very close to phosphine. And the depth of that dip could tell them how much sulfur dioxide was present in the atmosphere. If you then know how much it is, you then know how deep to expect the other dip to be that's very close to phosphine. And if you've got a dip that's deeper than that, then you know that that's the contribution from phosphine. And so that's what Greaves and collaborators did. They observed the other wavelength and said, there's not much there. You can't account for this huge dip we've seen at this wavelength where both phosphine and sulfur dioxide are. So we've definitely detected phosphine. But in this new paper, Linkowski and collaborators modeled the depth and shape of these absorption dips that you would expect and found that they could actually explain it completely with sulfur dioxide alone, as long as it was coming from much higher in the Venus atmosphere, 80 kilometers above the surface. Whereas Greaves and collaborators claimed that their detection of phosphine and sulfur was at 56 kilometers above the surface of Venus, not 80 kilometers up. And this is a big deal because 80 kilometers up the atmosphere is much thinner, you're much more exposed to radiation from the sun. If radiation from the sun hits into a molecule of phosphine, it breaks apart. And so phosphine doesn't exactly survive at those incredibly high altitudes, which means you would never be able to detect it at the strength that Greaves and collaborators claimed that they had, at least that high up in the atmosphere. On top of that, this study also realized that there was an issue with the ALMA data that had been missed by Greaves and collaborators. Now, ALMA is a very special type of telescope or instrument. So most detectors on the back of telescopes, what they'll do is they will observe an object like Venus, take all of the light from that object, and then make a trace of how much of each wavelength they've observed. ALMA doesn't do that though. ALMA can actually say, okay, in this area of the image, how much of each wavelength have I observed? And in this area of the image, how much wavelength? So you can see sort of spatially what the traces are. It's like getting a trace at every single pixel on the image. What that means though is that it makes your signal weaker. So, any absorption being caused by a gas like phosphine in Venus's atmosphere or like sulfur dioxide would be spread out across all of these different pixels, and you would assume that there is less there, like assuming there was less sulfur dioxide than there actually was. And so Lenkowsky and collaborators claim that if you correct for that weakening and that spreading out, you can actually explain Greaves and collaborators' ALMA observations, again, with just sulfur dioxide, and you don't need any phosphine. So that's two very convincing arguments for there being no phosphine on Venus. So I wouldn't blame you right now if you were just a little bit confused, because it's hard to know, like who to believe. Do you believe Greaves and collaborators' claims, or do you believe Lenkowsky and collaborators' claims? But I don't think we've heard the end of this yet, I think there's going to be more observations, more discussion, more analysis before we have any sort of definitive answer on whether there's phosphine on Venus or even life on Venus. Who knows? But this really is just science in action, and I love it. Phone that can do like a 3-second or a 10-second exposure, like, a lot of camera phones can do these days. Camera phones, how old am I? No, I'm good. Over the Martian atmosphere. And again, that's one of those things that will really help sort of pave the way for a possible redshift is essentially a measure of how fast the galaxies are moving away from us, because I can't even say astrophysicist. It's my own job title. If you cast your mind back to Sep 2012,